Piecewise C1 curves are going to be defined by putting together a bunch of C1 curves. So for that, we need to define concatenation, which the word is harder to say than the concept. Given two curves, gamma 1 and gamma 2, and we want gamma 1 to end where gamma 2 begins. So I just have gamma 1 and then here's gamma 2. And I want to put them together, so we will just reparametrize gamma 1 so that it goes from A to B, and gamma 2 goes from B to C, and then the concatenation of gamma 1 and gamma 2, which I'll write gamma 1, and I'll use this plus with a box around it, plus gamma 2 will be defined on the interval A to C. And it'll just be equal to gamma 1 on the interval A to B and gamma 2 on the interval B to C, and this will be continuous, again, by this condition, which ensures that gamma 1 of B equals gamma 2 of B. And we can similarly define the concatenation of finitely many curves. You just need to make sure that gamma 2 ends where gamma 3 begins all the way down the line. You can define concatenation of N curves. Note, it's no big deal to show that if you concatenate two curves, then the integral will be equal to the sum of the integrals of the concatenation whenever the right-hand side is defined, meaning both of these things exist. And we call a concatenation to be a piecewise C1 curve if all of the curves involved are C1. And so we have the tangent vectors of these curves existing at the endpoints, either from the right or the left, and that those tangent vectors don't have to agree at the points where you're joining them up, although their values do in order for it to be a continuous curve. So we can have piecewise C1 curves with places where it's not smooth, like these corners, but that's not a problem for this. And so many things that hold for C1 curves hold for piecewise C1 curves like this. So if gamma is a piecewise C1 curve now, this is just the earlier proposition where I put in the word piecewise C1 curve instead of C1 curve. So our integral of a one form along gamma is just computed this way. And we may have bad points where the curves join up, where these derivatives maybe don't exist, but those are finitely many bad points, so we'll just neglect those, and the Riemann integral doesn't care if you have finitely many bad points. And the same goes for this integrating a 1-0 form. Now, so this gives a way, if you can parametrize your curve, then you can, in theory, compute these, but how does this connect to anything we've been doing? Well, here's the main connection. Let U be a domain and assume we have gamma, a piecewise C1 curve mapping into that domain, and let F be an analytic function on that domain. And if we have the further property that F possesses an analytic antiderivative capital F on that domain. So this will give us sort of a fundamental theorem of calculus for integrating analytic 1-0 forms. So the integral of f dz over gamma will be given by taking an antiderivative at the endpoint minus that antiderivative at the starting point. And the proof just uses the fundamental theorem of calculus. So we only need to prove this on the C1 pieces of gamma, because you can reassemble all of the pieces together and you'll get a telescoping sum that will just give you this in the end if you can prove it for all the pieces. So without loss of generality, we'll assume that gamma is a C1 curve. And then our integral of f over gamma, we'll use the formula from earlier. I'll integrate from a to b. I'll have f of gamma times gamma prime of t. And this looks just like our general chain rule from a long time ago. So the derivative of, so we'll take our antiderivative with gamma plugged in, the derivative of that with respect to t. Well, since it's an antiderivative, capital F prime equals f. So this derivative here gives me back exactly what I want. But now this is just a typical calculus derivative dt of this function, although it's complex valued, that doesn't change anything. I'm just taking the t derivative of the two components. And so you'll get the change in the values. So I'll plug in b and I'll plug in a and I'll get their difference. So we have all this machinery just to kind of use this generalized chain rule and analyticity in these integrals, but it'll be surprisingly powerful. Let's look at a quick example of using this and kind of an intriguing question. Okay, so here's a polynomial. P of z equals 1 plus z squared plus z cubed. And let's integrate p of z dz on the line segment from minus I to I. So I'm just going minus I to I. And by the proposition, I don't need to parametrize anything. I just need to find an antiderivative, so that's nice. So I can find an antiderivative just like I know from calculus. So I'll have antiderivative of 1 is z, antiderivative of z is z squared over 2, and so on. And then just as in calculus, I'll evaluate it at I to get this, and evaluate at minus I to get this, and take their difference. And you end up with some value. So this is just to illustrate the concept, make sure we're on the same page. One question that we might use to kind of motivate material going forward is trying to estimate integrals like this. So let's consider the same polynomial, but I'm going to try to integrate p to the nth power dz. And now I know I can compute this in theory. I could just raise p to the nth power and compute things, find an antiderivative and evaluate the difference of 2 points. But it doesn't tell me a lot about how fast it would grow with respect to n. And let's see some simple ways to estimate it on the next slide.